Now let's discuss from rate laws to integrated rate laws. And the reason we're going to be interested in integrated rate laws is because integrated rate laws will allow us to determine the concentration of our reactant at any time that we want. And that's a useful thing to know. Now, remember that our rate law, if it's a first order overall and our reaction is just A to B, so it's first order, it'll be rate equals K, the rate constant, times A. And we also know that the average reaction rate equals minus 1 over the coefficient times the change in the concentration of A, that's delta, over the change in time. And what we're going to do is we're going to put these together and get, because this is the rate, so, one other thing we'll add is that the coefficient here is 1, so the coefficient part will go away. If you have any questions about what to do with a non-1 coefficient in this case, always happy to answer that, but it won't be an issue for us. So this is just going to become minus delta concentration of A over delta T. That's going to be the rate part, and it's going to be equal to the rate constant times concentration of A. And as we get ready to talk not only about the rate constant, which is lowercase k, but also the equilibrium constant, we'll talk about that next chapter, that's going to be capital K. And so what I'm going to start doing whenever I write my lowercase k's is making them cursive. So there, let's turn that into a cursive K. Okay, now for integration, what you need to do is instead of the deltas, you need to enter the differential form, which would be minus dA, concentration of A, over dt. And so that's going to be the instantaneous slope equals K times A. And what we can then do is separate it so that the A terms are on one side and the T terms are on the other. And so we're prepping this for integration for those of you who have had calculus before. And if you haven't, in this course, we just need the result of this. But just in case, and many of you will take calculus. So I'm going to separate this. I'm going to get the A term on the bottom here. So it's going to be the differential of A, concentration of A, over the concentration, equals K, and the dt comes up here, differential of T time. And I'm going to do one other thing. I'm going to move the minus sign to the other side, so I'm going to put a plus here and a minus there. This is now separated into the concentration of A and the time parts. So I'm now going to integrate both sides. And when I integrate both sides, I'm going to integrate from time equals 0 to whatever time I'm at currently. And at time equals 0, my concentration of A will be concentration of A sub 0. And that'll usually be given in the problem. And at time t, my concentration of A will be concentration of A sub t. And for those of you who have done integration, you know that when it's negative 1 power, when the concentration of something, or when the variable is in the denominator, the integral is what's called the natural logarithm of, in this case, concentration of A. And that's going to be from concentration of A naught for 0 to concentration of AT. And on the other side, the integral of dt is just going to be t, so it's going to be minus kt, where it goes from t equals 0 to t. So that's getting closer to our version here. Now we will do a definite integral here. That's what we're doing. We're going to now look at these limits. It's going to be natural logarithm of a at time t minus the natural logarithm of the concentration of a at time equals 0 equals, well, this term is going to be minus kt, and then it's going to be minus a negative kt, but t equals 0, so that second term cancels out. And believe it or not, we're getting close. So any two things that are natural logs or logs that are subtracted, you can condense them into a division under the same natural logarithm. There we go. And so this is the integrated rate law for first order kinetics. And this is particularly useful when you're using it to solve for time and you have the concentration initially and at some time. We'll derive another version later. Now, what does integration do? So if you've had calculus before, you know that. But we've seen in previous videos a graph of the concentration of some compound versus time. And what we generally see is that the concentration decreases with time. And now what what we had was that the reaction rate was the slope of this line. And we said there were two kinds of slopes. There was the average slope, where we took any 2 points and averaged over it, and the differential slope, which is what we just integrated, would be the tangent, also called the instantaneous slope. Now, the integrated rate law gives the equation for this line. And so we took the slope, we integrated, and we got the original equation that we needed. Okay? So that's what integration does. And now what I'd like to do is rearrange the first order integrated rate law that we derived on the previous slide into a more perhaps useful version. In order to do that, we have to take and get rid of the natural log term. And to do that, we're going to take the exponential of both sides. So we're going to take the what's called the e to the and e to the. So we're going to do it to both sides. So it's going to be consistent. And just like e to the ln x is similar to 10 to the log x, meaning that they're opposite functions, they cancel each other out. So 10 to the log x equals just x, and e to the natural logarithm of x also just equals x. So on this left-hand side, we get just these two, this division. And on the right-hand side, we get e to the minus kt. And one other thing we'll do, we will now move the concentration of A at time equals 0 up to the top on the other side. And this is a very useful version of the first order integrated rate law. Oftentimes in problems you will have the rate constant, you'll have time, and you'll have the initial concentration, and you will be asked for the concentration at some time t in the future. Okay? And this is what's called an exponential decay. And we'll talk more about that in future videos. Now, what we have to do next is go back to our natural log version of the first order integrated rate law and linearize it. And to linearize something means to put it into the form of a line, or let's say this, to put it into the form y equals mx plus b, which we know is the equation for a line. In order to do that, what we're going to do is we are going to separate this back out into natural logarithm of the concentration of A at time t minus the natural logarithm of the concentration of A at time equals 0 equals minus kt. And now I'm just going to move this natural logarithm of the concentration of A at time equals 0 term to the other side. Oh, yes, I'm going to do that. And I'm going to flip it all the way over here. So it'll be plus on the other side. And I prefer to keep it like this, even though we have a negative sign here, because it wasn't that hard. We're done. This is the form of the equation of a line. So if I write under it y equals mx plus b, I can see that my y is going to be the natural logarithm of the concentration, that my x is going to be t time, which means that if I plot the natural logarithm of the concentration of A versus time, I will get a straight line. And what I should add for us is that I will get a straight line if the reaction follows first order kinetics. So, and I'm going to write that here. Let's see, I have some more things to do here. So, I think this is the best way to put it. If the plot of the natural logarithm of concentration versus time is linear, then the kinetics are first order. Or let's say this, the kinetics follow a first order rate law. And as we've seen, a first order rate law says rate equals k times concentration of A to the first power, but the 1 doesn't have to be written. Okay? And additionally, so if now I make some other assignments, so the slope of this line is the negative of the rate constant. So we can do a plot and get our rate constant. And here the y-intercept is the natural logarithm of the initial concentration. And I just want to write here, this is the y-intercept. Okay. So, and we're going to do this. This is all for the first order integrated rate law. We've got two versions of the integrated rate law, one with natural logarithms and one with exponentials. And we've now just shown how to linearize an equation for the first order integrated rate law. Okay. I think that's everything. Good. Oh, nope, one more thing. So, especially for exponential decays that are first order, that exponential decays tend to be first order. So let's define something called the half-life. The half-life is the time in which half of the reactant is gone. And so it's denoted T sub half, and it's the time, its concentration equals half. And so what else we can say about this is that this is true for all integrated rate laws. And you can derive an equation for the half-life for all of the integrated rate laws we're going to see. But we're going to start by working or continue to work with the first order integrated rate law. So for first order, we know that the first order integrated rate law says that natural logarithm of the concentration of A over initial concentration equals minus kT. And now we're just going to plug these terms in here. So T is going to be T to the 1/2. And A, or A of T, is going to be half of our initial concentration. So there we go. And so these two parts cancel out, and we're left with natural logarithm of 1/2 equals minus K times the half-life. And then I'll bring the K, I'll actually plug in a number here for, where did my calculator go? There we go. So ln of 1/2, I'll enter 0.5, and then I'll hit my ln button here, minus 0.693. So redoing this, it's going to be minus 0.693 equals minus K times the half-life. Bring the K over to the other side, cancel out both of the minuses, and you get an equation that says that the half-life is equal to 0.693 over the rate constant, like so. And that is good only for first order integrated rate law, or let's say only for first order, as is everything that we've done so far. And we'll talk about this more, but if we were to do that for 0, first, and second order, we would get a table that looked like this. And so this is a summary. And we'll talk more about this, but so the rate law for first order says rate equals the rate constant times your initial concentration. The concentration is raised to the 0th here, so it goes away. That's 0th order. Here's second order, and these are the three main rate laws that we're going to look at in this course. Then we saw our integrated rate law, and we get those for all of these. We have units of our rate constant, and the linear plot, remember we said natural logarithm of A, concentration of A versus time was linear, and our slope Anyway, we're going to explore all of these and some of the examples that are coming up.